Greetings, AP Statistics students. You may recall that a few days ago we started to take a look at the sampling distribution for a difference in population proportions. Today we're going to construct and interpret confidence intervals for a difference in two population proportions, and we'll also be doing a hypothesis test for a difference in two population proportions. So we began a few days ago to look at this example where we had two separate groups of randomly selected U.S. adults. One group was 1,024, and 50% of that group approved of Obama's job performance. And the other group was from 2009. There was 1,110 randomly selected U.S. adults, and 53% of them approved of Obama's job performance. So in 2009, we were at 53%. 2010, a year later, 50%. So some would argue that the approval rating went down. But remember that if we took a different sample of 1,024 and 1,010 adults, we would probably get a different sample statistic, a different difference than 3%. So our idea here is that we're going to construct a confidence interval to get a range of plausible values for the true difference in population proportions. So we'll get a confidence interval for the change in Obama's approval rating among all U.S. adults. And we already checked the conditions in a previous class. We have two independent random samples. It's reasonable to assume that we've sampled less than 10% of both of those populations. And here we have our large counts condition. We have at least 10 successes and 10 failures in each group. We have at least 10 people that approved of Obama's job performance, and at least 10 that did not approve of his job performance. So let's take a look at constructing our two-proportion z-interval. If you recall, the general way to construct a confidence interval is to take your sample statistic, which is your point estimate, and then you add and subtract your margin of error. Your margin of error is made up of your critical value and your standard deviation of your statistic. This is our general recipe for constructing a confidence interval. So for us, our statistic is the difference in the two sample proportions, so p hat 1 minus p hat 2. Our critical value is based on the z statistic, or I should say the z distribution. So we have a z star value, and then the standard deviation of the statistic is found with this formula, and we talked about that formula a little bit in a previous class. So I'm going to substitute in the values for p hat 1 and p hat 2, 50% and 53%, and substitute in our sample sizes. We are also going to substitute our z star value. Our z star value is based on the 90% confidence level. If it was a 95% confidence level, instead of being 1.645, this would be 1.96. Recall that you can get the z star values from using the infinite degrees of freedom row in your t-table. So now let's actually see what the confidence interval is. Here we actually have our confidence interval. Our lower bound of our confidence interval is negative 0.0661, and our upper bound is positive 0.00674. That's our actual interval, and our interpretation is that we are 90% confident that this particular interval here captures the true change in the approval rating of Obama for U.S. adults during the time period mentioned. So our question now becomes, what about part B here? Based on our interval, is there convincing evidence that Obama's job approval rating has changed? The headline would be that it's down 3%, but what would our interval tell us? Well, notice that our interval has both negative values and positive values, which means that 0 is in the interval. So since 0 is in the interval, it's possible that the approval rating has not changed. For the approval rating to have gone down, we would need to have both of these numbers be negative. For us to have convincing evidence that the approval rating has gone up, we'd want both of these numbers to be positive. Let's take a look at how you would do this on your graphing calculator if you'd prefer to do that rather than substitute the numbers into the formula to actually construct the interval. So on our graphing calculator, we're going to go to Stat and then over to Tests, and we're doing a two-proportion z-interval. So that's right here, option B. And notice we have x1, n1, x2, n2. Those are the number of successes in each group. And we're also going to be entering our sample sizes. So the number of successes in the first group was 512 out of 1,024. That is the data that came from 2010. And then we have the data from 2009. We had, let's see, it was 53% of the 1,010. Right. Notice that this is a decimal value. We need to change this to a whole number value, or our calculator will give us an error message. So make sure you change that to a whole number value, the nearest integer. And the sample size in our other sample is 1,010. And we're constructing a 90% confidence interval. Go down to calculate, and we can see the value for our lower bound and our upper bound, as well as our sample proportions and our sample sizes. Now let's take a look at an example involving a hypothesis test for two proportions. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers between 1988 and 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005 and 2006, 19.5% showed some hearing loss. So yes, this is a difference of 4.5%, but is this convincing evidence that the proportion of all teens with hearing loss has actually increased? So remember, if it says do these data or does this data give convincing evidence, you're doing a hypothesis test. To begin, let's define our two population parameters. P1 is the proportion of teens with hearing loss, so the true proportion of all teens with hearing loss from 1988 to 1994, and P2 will be the proportion of all teens, the true proportion of all teens with hearing loss from 2005 to 2006. So our null hypothesis is that there is no change or no difference in the population proportions. For our alternative hypothesis, we have to decide, is this going to be a one-tailed test or a two-tailed test? And the clue to whether this is going to be a one-tailed test or two-tailed test is right here in the word increased. So we can tell that we have a one-tailed test. The question is, do we want to use less than or greater than? And whether we use less than or greater than in part depends on how we defined our population parameters. If hearing loss has increased, we'd expect P2 to be bigger than P1, or we could say P1 to be smaller than P2. So we really want to see if P1 is smaller than P2. And that would indicate that the proportion has gone up. The proportion of all teens with hearing loss has increased. Next, let's check our conditions. So our simple random sample, independently selected simple random samples. We have two independently selected random samples of teens. We've sampled less than 10% of the population, and our large counts conditions have been met because in our two samples, we definitely had at least 10 successes and 10 failures. We had at least 10 teens showing some hearing loss and at least 10 that did not show some hearing loss. So let's actually now calculate our test statistic and get our p-value. Remember that the general formula for a test statistic is statistic minus parameter divided by standard deviation of the statistic. Here we are doing a z statistic. And if you recall, the standard deviation of the statistic is found by this formula when we're working with confidence intervals. However, here we are going to assume that P1 and P2 are equal. That's our null hypothesis, that the two population proportions are equal. So we actually have to use a slightly different formula here. We're going to do a combined proportion of successes. So if you take a look at this formula, you'll see that we have the total number of successes in each group 450 and 351. And we have our total sample size, 3,000 plus 1,800. So this gives us a combined proportion. This was the proportion of the teens in the two groups combined that experienced some hearing loss. You'll see this number appear in our formula for our test statistic in a moment. So here's our test statistic. We have our proportion of teens that experienced hearing loss in our 1988 to 1994 sample, and the proportion of teens who experienced hearing loss in our 2005 to 2006 sample. Notice that we have a 0 here, and that's because if there is no difference between the two groups, we would expect P1 and P2 to be equal, or if they're equal, their difference would be 0. Sometimes you'll actually see the null hypothesis written this way instead, which if you think about it makes sense because this is algebraically equivalent to P hat 1 equals P hat 2. You also sometimes might see the alternative hypothesis written in a similar way, P hat 1, or I should say P1 minus P2 less than 0. Once again, moving the P2 over to the left side of the inequality. Notice here the 0 is indicating that there's no difference, that there's no change. Most of the time, this value here will be 0, unless you are testing to see if there was a certain size of difference. But most of the time, this value would be 0. Then notice that in place of P1 and P2 here, we're actually using our combined proportion value. So when we actually do this calculation, we get a z-score of negative 4.05, or I should say a z-test statistic of negative 4.05, which if you recall from the 68, 95, 99.7 rule, once we get beyond 3 standard deviations, we're way in the tail of our distribution. So it makes sense that our p-value is essentially 0. So since the p-value is essentially 0, we can reject the null hypothesis. We have very strong evidence that the proportion of teens with hearing loss has increased. However, because this was only an observational study and not an experiment, we can't blame iPods for the increased hearing loss in teens. This last part is essentially what question B is asking. We can't infer causation because we did not do an experiment. This was just an observational study. Surveys are examples of observational studies. Before we finish this screencast, let's just see how this would work in terms of our graphing calculator. So let's go back here and go to Stat, Tests, and we're doing a hypothesis test. So we need to find a 2 proportion Z test. Here we go, option 6, 2 proportion Z test. And notice that here we have the numbers from our previous example. We need to enter the numbers from this example. We had 450 teens in the first group of 3,000 that had experienced some hearing loss. And then in our second group, we had 351, 19.5%, in the group of 1,800 that had experienced some hearing loss. And we want less than, so that's already chosen. I'm going to go down here to draw. And we have our normal distribution. And notice that because our p-value is so small, we don't really even have any shading on this diagram. Notice also it says p equals 0, and that's probably because actually it's something like 0.00000001 or something like that. And since this can only display up to 3 or 4 decimal places, it rounded that to 0. Notice that if instead of doing draw, you actually went down to calculate, you can see that the p-value is 2.58 times 10 to the negative 5th approximately. Notice also it gives us our combined p-hat value here, our combined proportion of successes. So we will be taking a look at several examples in class over the next couple days for both proportions, and then we'll be also moving on to working with means. I hope you enjoy your snow day.